Hello everyone, my name is Ryan Wan, and for my literature review for ECEC 572, my topic is energy efficient circuit design, and I will be specifically focusing on full adders and various other arithmetic units. So just a quick overview of what we'll be talking about today. First, I'm just going to be going over a short introduction on full adders and their standard structures. Then we're going to be talking about where possible optimizations may lie. First, in the logic structure or the general flow of how the adder works. And then in the logic style, which generally consists of changing what the adder is consisted of. And then we'll talk about various implementations from different papers regarding this topic, and finally some conclusions after we've gone through all the implementations. So first, again, we're just going to start with a small introduction on the full adder. Right. So the background on why I chose to focus on full adders is when looking at generally increasing the efficiency of a system, one small piece that you can increase the efficiency of in terms of power and speed and have an overall increase is the full adder. It's a versatile and common component, and it's used in various locations. So if you want to optimize any of those, you can start with the full adder itself. Any multi-bit adder, such as either serial or parallel, they all utilize the full adder, as well as carry out multiplication, and of course in the processor, there's a lot of usage of the adder there with the ALU, any floating point or any address generation, all requires the full adder. So optimization in terms of both speed and power for the full adder can lead to massive gains for the system. So that's why I chose to focus my energy efficient circuit design on specifically the full adder. So now here's just a small overview of the full adder. The basic full adder structure is you have two half adders and an OR gate, or if you break that down completely to gates, you have a XOR gate and an AND gate in each half adder that leads into another XOR and AND gate, and then you have an OR gate for the carryouts. And on the right side, I just have the truth table, just showing the bits for each. But yeah, this is just a general CMOS full adder implementation. And if we look at the next side as well, this is just a general transistor look of the design, right? We have 28 transistors, and I know there might be like small differences here and there of how it's laid out, but this is what's generally considered the standard, CMOS design. Of course, we're going to talk a little about this more later as well, but when changing logic styles, a lot of the changes happen here in terms of in the makeup and what's used, what technology is used here. Right. So first, we're going to talk about logic structures in terms of where we can really improve our system. Right. So again, I pulled up the diagram of the full adder circuit. Right. The general logic structure or the logic flow of the classic CMOS full adder is that in your first block, that's when you take in your inputs A and B, and the output of that is a XORing of A and B. And then your second block takes that output as well as your carry in and calculates your sum. Meanwhile, your third block takes out that output as well as the carry in and as well as the A term, and it gets your carry out term. Right? So if you take a closer look at this structure, what you'll realize is both block 2 and block 3 rely on having to know what the output of block 1 or the XOR of A and B are in order to actually move on. Right. So in this logic structure, the overall propagation delay and the power consumption, they basically rely heavily on this first block. Right. This first block has a heavy influence on the entire structure. And so while if you may want to keep this structure, then you may think to increase the efficiency of this first block. If you were to change the logic structure, you might do so in a way where both block 2 and block 3 are reliant on block 1. And below, the classic 3-block structure of the full adder, we'll talk about this alternate structure more, but this is just an example of an alternate logic structure and what it might look like. It still has the same inputs and same outputs, but how it goes about and how it organizes all these inputs and outputs these are different. So that's what you would do if you want to change the logic structure. Next, we're going to talk about different logic styles. So when I'm talking about logic styles, generally this is changes at the gate and transistor level, and trying to gain efficiency and speed by modifying these. Of course, you can also adjust the logic structure as well, and some of these will require a change to the logic structure, but it's not necessary to adjust the logic structure, and a lot of the early papers we'll be looking at later on, the implementations, look to change the logic style while maintaining the same logic structure. So now I'm just going to quickly talk about each of these different logic styles, just to give a little introduction in case you're not familiar with these logic styles, so that when we talk about the implementations, we're more familiar with what's actually going on in those papers. So the first, again, we're just coming back to our standard CMOS, complement metal oxide semiconductor, right? And since generally we know what CMOS is like, we see on the right. We'll talk about what are the advantages and disadvantages that CMOS has over many of these other logic styles, right? And the advantages is, number one, it's very easy to implement and it's reliable, right? And on top of that, it has excellent noise margins. So then, if CMOS was perfect, of course, we wouldn't be pursuing other logic styles, but CMOS has its own flaws when it comes to creating smaller circuits. And so if we look at the disadvantages, of course, there's significant area size because you have to size up generally the PMOS transistor to match for the gate, and so you're left with, significant area size, and in general you'll find CMOS circuits will have a much larger area than some of these other logic styles. As well, for the same reason, we have a high input capacitance for CMOS, and generally we have a higher power dissipation. Now this isn't set in stone, but when we compare bare bones CMOS to bare bones of other styles, we do find that CMOS has a higher power dissipation. So now we'll talk about our first alternate logic style, and that's the complementary pass transistor logic, also known as CPL. Right? So CPL is a pass transistor logic where it utilizes only NMOS transistors, right? And then the output of the NMOS transistor network is connected to an inverter. Right? So as you can see in our top diagram on the right, this is an example. We just have the NMOS in the system that goes out to the inverter, right? And so the advantages of this is because you only have the NMOS per gate instead of both, right? Instead of both the PMOS and NMOS, you have much smaller input capacitances, and you do not need to size the pull-up or pull-down transistors, right? And because of that inverter at the output of CPL circuits, we have good output drive compared to many other logic styles. However, we do have a higher static through current, and while this looks like it has less transistors and it's an easier layout at a lower level, it actually gets much more difficult generally as you increase in the complexity of the circuit designing. It looks relatively simple in less gates right now because of it's just a simple gate, but as you increase the complexity, it's harder to implement and relatively inefficient. Maybe not compared to CMOS, but compared to some of the other pass transistor styles, which we'll talk about right now. So an alternative to the CPL is the double pass transistor logic. So this is another usage of the pass transistor logic. However, instead of using only NMOS transistors, it also uses PMOS transistors as well. And you can see that on our figure on the right that it has PMOS transistors as well. Now, the introduction of these PMOS transistors causes some major changes and gives some big benefits to the DPL structure of a CPL. Namely, you can use much lower supply voltages and there's much lower noise and delay. However, again, we're back at the problem of higher input capacitance since we're using both PMOS and NMOS transistors. And another alternate style, which didn't warrant a slide for itself because it's not as widely used, is the swing restored pass transistor logic. This is essentially CPL that's slightly modified. It has a latch type swing restoring circuit that has two cross-coupled CMOS inverters that generally leads to a little bit of higher performance than classic CPL. It's not used too widely, so it didn't warrant a slide for itself. We continue on. Transmission logic. We'll talk about this briefly as well because it is an existing logic style. However, in the modern adders, it's not really used. It's used in a lot of the earlier adders. It's based off of transmission function theory in gates, and the result is the transmission function adders and transmission gate adders, right? And because of its usage of transmission theory, it has inherently low power consumption, when you compare it at base to many of the other logic styles. However, the disadvantages are that, it does lack driving capability when it's compared to CMOS and CPL or DPL styles. And this is because the inputs are tied to the outputs, and so very low driving capability. And so, while it may have inherently low power consumption when it's by itself, it has poor cascaded performance when you chain these adders together, which you often need to do to form some of these other parallel or serial multi-bit adders because of this low output driving capability. So we'll talk about this later in the implementation, some of the early implementations, but eventually these don't show up as often. And we'll briefly talk about Domino as well. This is not very common, but it is an alternate logic style. The reason it's not used is because it's a dynamic technique, right? And of course, dynamic techniques, they have their benefits, right? However, dynamic techniques, while they generally lead to higher speed in CMOS, they're not suitable when you're trying to go for a lower power circuit because of the large clock loads and the high switching activities, right? And so even though you get rid of the static power dissipation, it's overall less power efficient. You have more power dissipated, especially with the clock distribution network. So there's some very early implementations using domino logic and dynamic techniques. However, that's it's found to be not as efficient, so it's not as common. And finally, we have what is the hybrid logic styles. So hybrid is generally a combination of different styles that we mentioned before, and the most common hybrid combination is taking one of the past transistor logic, CPL or DPL, and combining it with CMOS in order to try to get the benefits of both. So now that we know, generally what all the different logic styles are like, we can actually go through and look at each of our papers and see how they performed. And we're going to be going in chronological order just because, a lot of these papers are also comparing to each other. So by going in chronological order, we can see how certain adder structures compare to future developments. Right? We're going to start all the way back in 1995. This might be before any of you were born, but this 1995 paper just does a bare bones CMOS, a CPL, DPL, and domino comparison, with the domino being both dual rail and single rail. Right? So this comparison wasn't done as a single full adder, but actually it was a composition of those full adders into a 32-bit carry look-ahead adder. And if you remember what we talked about, chaining together for transmission circuits ends up very poorly, which is why transmission theory based adders were not included in this study. Right? And if we just look overall at the general statistics here, and we look at the power, we can see, first of all, both the dual rail domino and single rail domino have much higher power consumption than their static counterparts. Almost twice that of the static counterparts. And of course, static here at the first column refers to static CMOS, but much higher power consumption. They do have a little bit of a lower delay, but that power consumption, it really hurts them there. It doesn't warrant the smaller delay they have. And in addition, they have much larger area as well. So if you look at the total transistor width, is much larger than CPL and DPL, while slightly larger than static. And if we compare the static CMOS to both of the CPL and DPL, power-wise, static and CPL perform around the same, although CPL can have a little bit of a shorter delay. But again, for CPL, that real bonus is in the speed as well as the transistor width. And as you can compare, the CPL transistor width is much smaller than the static, so it'll be taking up a lot less area. Now, on the other hand, for DPL, DPL has a lot of the advantages over CPL in terms of power, speed, and delay. And we can see that reflected here, as DPL has a decent, but here it's the most power efficient, right? And it has the lowest delay out of all these static components. But again, because its usage of PMOSFETs as well is slightly larger than the CPL, while being still in the static. So this was just a good comparison of these basic techniques when the full adders are chained together into a larger system. Right. So now what we're going to look at here is a hybrid pass logic full adder, right? So this study did only looked at a single 1-bit full adder, right? And this is the first introduction of hybrid pass logic, right? And if we look on the left here on our figure, this is the general structure of the adder we're using here. And as you can see, they do have 3 modules, right? 3 blocks. The first block takes in the first 2 inputs. The second block takes the output as well as the carry in, and the third output takes in the the second output takes in the carry in as well as the output of the first module, and the third module takes the output of the first module as well as outputting the carry out. So while the structure is the same, what happens inside the modules is completely different because they're using a hybrid logic inside of these, right? If you look at module 1 and module 2, that's not standard CMOS, right? We're using pass logic, right? If you look at module 1 and module 2, in module 1 they're using XNOR and XOR, right? Instead of the classic half adder of just XOR and AND, right? And now if you look at the right, we can see the power versus the supply voltage, and this hybrid version, performs admirably, in comparison to all the other ones. It still performs, a little bit worse than the standard CMOS. But in comparison to the TFA and TGA, which are briefly mentioned here, as we mentioned before, are based on transmission. It does perform better than those as well as CPL. And then if we look at the power delay product, right, this is just the power delay. It's just a way of measuring both the power and delay in aggregate, as well. It has very good performances as your supply voltage goes up. Not great at these lower voltages, but overall it does have a higher output drive than your classic CPL. In part thanks to using a static CMOS, and it does have a much reduced area compared to the traditional full adder. You can just see, just looking at model 1 and 2, only 6 transistors used, so it's much smaller and has a smaller reduced area compared to the classic static CMOS. So it starts to get the best of both worlds, and really this starts the ball rolling in terms of hybrid styles, right? So now this hybrid CMOS logic style is a modification of that paper, right? If you look at our table here, we can look at the simulation results. They simulated at a 50 megahertz frequency, and they did it at a single supply of voltage. Then we have the static CMOS, of course, with 20 transistors. The CPL that they compared has slightly more transistors. They do have the TGA and TFA, of course. They do have better power than CMOS and CPL, because as we mentioned, when you're looking at just a single adder, they do have pretty good power consumption. And then we have this HPSC, which is the previous one we're comparing to. So the previous one we just looked at from 2003 is referred to as HPSC, these future ones. And a new HPSC was basically a small, improvement of the previous one, which is not included in this presentation. But then we can see the proposed one, right? So the proposed one actually works very similar to the last one as well. It uses the same logic structure as module 1, module 2, module 3. With that hybrid structure, it just adds a couple transistors compared to the HPSC, right? And mostly I'm going to be comparing it to the HPSC. We see it has 2 more transistors, but 7 nanowatts less power, right? Almost half the delay, right? Which leads to almost half the power delay product. And in terms of area, it's an improvement as well. So yeah, this as hybrid CMOS logic styles were researched more, we can see that they're starting to outperform standard CMOS and CPL counterparts. And then in 2008, right, what was introduced was CPL, right, with a brand new logic structure. Rather than using the classic module 1, module 2, module 3 logic structure, this was a CPL that used level restoration, as you can see in the logic diagram, in order for its logic structure. Right? And this change of logic structure really paved the way for CPLs and TPLs to start dominating. Right? As you can see, the top simulation results is the power. The table 2 is the delay. Compared to the hybrid that we looked at from 2006, right, the CPL does perform relatively better. Compared to a static CMOS, it does have a higher power consumption. But if you look at the delay, however, it's much faster in terms of the delay in comparison to both hybrid and CMOS. And that's thanks in part to its logic structure, right? And using this logic structure in a classic CPL and the classic logic structure has a higher output drive, and it has reduced transistors for larger applications. On itself, in this single full adder, right, which is the test they did, it does have more transistors than a CMOS or a hybrid. However, based on how it's designed, when you're chaining these adders together, it actually has reduced transistors for these larger applications and increased speed over classic CMOS. Right, and so that really paved the way for this 2011 paper that has some of the best statistics when it comes to speed. Right. So first, we're going to look at the logic and structure. They have 2 new proposed full adders, right, that both use a brand new logic structure. And the first one uses a DPL logic structure, Second one, as we mentioned before, briefly, is a swing restored CPL logic style. So essentially, we have a DPL and a CPL style. So if we look at the structure, right? So what they did here was they got rid of the necessity for the sum out and the carry out to rely on that single output product. Instead, they have a XOR and XNOR feed directly into the multiplexer and or feed directly into the other multiplexer, and one takes the input from the other, which goes to carry in, goes into both multiplexers, right? And so this is a brand new logic structure that they implemented for both this DPL and CPL logic styles. And if you look at their performance just blows all the previous ones out of the water. Right? If you look at HPSC, that's the 2031 that we looked at. The hybrid CMOS is the 2006, and the new CPL is the 2008 we look at. Right? Top refers to the entire test benches, statistics, and FA refers to just the full adder. But if we just look at it across, right, in terms of both power, delay, area, it's just huge improvements, right? Compared to the HPSC, all these are a comparison to the worst case, but 80% power savings and 25% speed improvement, which leads to an 85% power delay product optimization, right? And even comparing just to the CPO, which is the newest one, there's a decent reduction in the power, especially just for the full adder, right? Almost 100 less watts, right? The layout of the table is a little weird, but the units are at the top. It's 100 less in megawatts, right? So that's a huge increase, right? And much reduced delay as well. So this new logic structure for the DPL and CPL works so much better. And as well, the important thing is the area was optimized as well. When generally, this is a struggle as you use DPL as it gets more complex. Generally, the area gets worse in the CMOS at sometimes, but the area is optimized here. And importantly, the minimum power supply voltage was reduced to 0.6, which is nothing new. This is something the CPL introduced as well, but comparison to our different hybrid and the HPSCs, it's a huge reduction of the minimum power supply voltage. Alright, and then this is the most recent one that we have here. It's just a comparison now of CMOS, CPL and DPL. However, it's a comparison of them into a larger structure. So here we see a comparison of them into 16-bit CMOS, CPL, and DPL adders. Right, and this is, instead of just looking at one single use case as we did before, we're looking at different adder schemes. So we have a ripple carry adder, carry look ahead, carry save, all these different adders that are 16 bits, and we can do a comparison of CMOS, CPL, and DPL. As we mentioned before, a head-to-head comparison of CMOS and CPL, we see sometimes the transistor count is even. Sometimes CMOS has more and sometimes CPL has less. And again, this is based on the fact on how this newer CPL, based on how you're chaining the adders, it can lead to less transistors. But it also relies on the structure of whatever combination of adder you're creating. Right, and DPL in general, of course, I think as we're slowly realizing, DPL is just much better than CPL and CMOS in terms of transistor. And even if we look at the power, right, it's much more power efficient, and generally the delay is much better as well. Delay is much higher for the CPL based adders. So after we look at all of these, right, we can have conclusions, right? So at the beginning, right, we had a lot of just a comparison of bare bones adders, using the classic logic structure. However, we had an introduction of hybrid-based adders, right, that try to take the best of CPL and DPL and speed and area while getting the CMOS drive and power. Right? And for a while, right, and for most of from 2000 to 2008ish, right, these hybrid-based adders had the best performance. However, with adjusting the logic structure, the classic logic structure, this turned out to be the key in order for CPL and DPL to perform better, right? And it led to higher speed and less area, right? As well as improvements on the weak points normally of the output drive, as well as power efficiency. And these are starting to outperform hybrid-based adders, and currently are still the best, performing single full adders. And so yeah, this is my project. It's just showing you guys a little bit of interesting information on power energy efficient circuits for full adders, and generally what the techniques have been behind finding the most energy efficient circuits. So thank you for listening.